Hello, this is a calculus video. We're at the beginning of James Stewart's chapter 8 in his 6th edition. The chapter is called Techniques of Integration. And before he dives into integration by parts and so forth, he has a nice little summary of some stock integrals, some basic integral formulas that you should have well at hand as you go about this path of integration. Again, I am following James Stewart's 6th edition and beginning on chapter 8, Techniques of Integration. Okay, so let's dive in. So basically, integrals are antiderivatives, right? They're the reversal of derivatives. I personally find derivatives fairly easy. Integrals are a little bit harder. There's not a stock pattern or formula to integration. It requires a little bit more creativity. But basically, integration is reversing the pattern of a derivative. So let's review some of the key derivatives. This is one of the key derivative formulas. When you're giving the derivative of something raised to a power, you multiply the front of the variable by the power n, and then you subtract 1 from the power. So the derivative of x to the n is n times x to the n minus 1. Okay, that's fairly easy, one of the very first derivatives. So how do we work backwards from that? How do we do the integral of a power? Well, we're gonna do such that if we multiply the power by the front and subtract 1, we'll get x to the n. It's the reversal, kind of going backwards in reverse motion. So if you take the power n to the, x to the n plus 1, if you take n plus 1 and multiply it by the front of x, you're going to have n plus 1 divided by n plus 1, which is 1. And so that leaves you with x. And then if you subtract 1 from n plus 1, you get n plus 1 minus 1, which is just n. So you can see that this particular formula, x to the n plus 1 divided by n plus 1, when we apply this, it ends up as x to the n. Now, we have to put a constant there because, of course, the derivative of constant is 0. So we don't know whether there was a constant, but basically, constant could be 0. But the integral of x to the n is going to be x to the n plus 1 divided by n plus 1 plus some constant. Okay, so this is the straightforward reversal of the derivative of x to a power. All right, so this is a formula that you should know. Here's another one. What about e? Again, this is fairly simple because the derivative of e to the x is e to the x. So the integral of e to the x is going to be e to the x plus a constant, because, if you take the derivative of a constant, it's going to be 0. So again, very nice and easy, right? Something to know. Let's keep going, right? I wish it was all that easy. What about the natural logarithm? Well, we know that the derivative of the natural logarithm of something is 1 over something. So that tells us that the derivative of 1 over something is going to be the natural logarithm of something plus a constant. All right? So natural logarithm and 1 over x are in derivatives and integrals, they're the reverse in that reverse relationship as well. Let's keep going. Not hard so far, right? Oh, here's another one. The integral of a to the x is going to be a to the x over the natural log of x, natural log of a, plus some constant. Why is this so? Because the derivative of a to the x is a to the x times the natural logarithm of a. And so if you go the reverse direction, the natural logarithm of a cancels out. Okay, things to memorize, to stick up here for a rainy day, a rainy integration day. What about sine and cosine? Well, the derivative of the sine of x is the cosine of x. The derivative of the cosine of x is negative sine of x. Okay, so with derivatives, these reverse. So that makes it pretty easy because the integral is just going to be the opposite. But we have to pay attention to the sign. So if the derivative of the sine of x is the cosine of x, then the integral of the cosine of x is the sine of x. And you'll remember there was no sine, or I mean by sine I mean plus or minus, not sine, S-I-N-E. With the sine, the integral of the sine of x, which we're going backwards here, we're going to have to put a negative sign in front of the cosine of x. So it's the exact opposite. The derivative of the cosine of x is the negative sine of x. So if we're doing the integral of the sine of x, it's going to be the negative cosine of x plus a constant. Again, not too difficult things to take up your brain space. What about tangent and cosine? Cotangent. Now it's going to get a little bit more complicated. The derivative of the tangent is the secant squared x, and the derivative of the cotangent is the negative cosecant squared x. Okay, so you got to memorize that. That's not as easy to memorize. But once you have that, the reversal shouldn't be that difficult. The integral of the secant squared x is going to be the tangent of x plus a constant. And the derivative of the cosecant squared x is going to be the negative, get the negative out there, of the cotangent x plus a constant. All right, getting a little bit more difficult, taking a little bit more brain space, but still not too bad. All right, keep going. Hyperbolic functions. Hyperbolic functions are treated in the 6th edition of Stewart in the latter part of chapter 7. The hyperbolic functions are basically the hyperbolic sine is e to the x minus e to the negative x over 2. And the hyperbolic cosine is e to the x plus e to the negative x over 2. Okay, now that's something to remember. However, the integrals of them, the derivatives of them are very easy because the derivative of the hyperbolic sine is the hyperbolic cosine, and the derivative of the hyperbolic cosine is the hyperbolic sine. They're interchangeable, don't even have an opposite sign, plus or minus, I mean. And so therefore, the integral of the hyperbolic sine is the cosine, hyperbolic cosine plus a constant, and vice versa. Okay, so that wasn't too hard. Tangent and cotangent. Well, this is a little bit more involved, but the integral of the tangent of x dx is going to be the natural logarithm of the secant of x plus a constant. Just memorize it. Similarly, the integral of the cotangent of x dx is going to be the natural logarithm of the sine of x plus a constant. Just memorize it or look it up, right? Hopefully you have a chart nearby, like the one back here. I think I took this from Union math department. Anyway, just memorize these or have them close at hand. Finally, 2 more, and these are a little bit involved, but when you're doing the integral of a rational expression, rational being something over something, this might be something to have nearby to pull up. The integral of 1 over x squared plus a squared dx is 1 over the a tangent to the minus 1, the inverse tangent, times x over a plus a constant. Again, this was covered in the latter part of chapter 7 when he was talking about the derivatives and integrals of the inverse trigonometric functions. Here's one last one for this video. If you have a rational function involving a square root in the denominator, the integral of 1 over the square root of a squared plus x squared dx is the inverse sine times the inverse sine of x over a plus a constant. All right, well, this has been a quick review of some of the stock integration formulas that you want to have at least on the tip of your brain, that James Stewart starts off his chapter 8 with this quick review of some of these general ones. I'm kind of excited. I'm thinking about going back to school, a little bit online, one at a time, and I'm actually signed up to take a Calculus 2 class this fall in the beginning, first part of it. We'll see what happens. Hopefully a lot of it will be review, but anyway, so this is why I'm revamping or restarting up some of these calculus videos this July of 2021. All right, well, have a lovely day with these basic integration formulas.